Thanks for inviting me. Since I'm the first speaker in the workshop, I'll start with a brief motivation to the topic. So, everybody motivated? OK, so now we can continue. It's a slightly outdated pile of slides, but yeah. OK, I'm going to talk about neural networks, which I guess most of you are familiar with. But just as a brief reminder, we're talking about predictors which can mathematically be written as a sequence of linear transformations followed by nonlinear transformations. Given some data, we tune the parameters of the linear transformations, parameterized by these matrices W's and vectors B, and hope that we get a good predictor, and usually we do. And I'm going to focus mostly on the optimization aspect here. And the big question is the following. So, we're given some network. We have some data distribution. Could be some population loss or some finite data that we want to be good on. And we essentially try to solve this kind of problem. And the main challenge is that it's, in general, very non-convex in our parameters. Non-convex functions cannot be optimized in general. On the other hand, these neural networks are successfully trained with very simple gradient-based methods, such as stochastic gradient descent. And the big question is, why? Why does it succeed? So what can we say about this kind of optimization problem? So the kind of ideal result we might want to have is that we take the algorithms actually used in practice, and we run them for polynomially many iterations, polynomial in the relevant parameters, and we indeed find a nearly optimal solution. Unfortunately, even for some very simple networks, this can be a very difficult result to achieve, and we'll see some examples of this later on. But as theoreticians, we still want to prove something, and one standard trick is to change the question. So maybe we won't show this kind of algorithmic result, but more something about the niceness of the geometry of the objective function. For example, that maybe it's non-convex, but there are no non-global local minima. And if this phenomena occurs, it means that if we run some gradient-based method and converge to a local minimum, it means that we found a global minimum. And it's widely believed that finding local minima as opposed to global minima is something that is easier to do with gradient-based methods. On the other hand, if we do have spurious local minima, then our life starts to become more difficult. Maybe we can still show something, but we need to start understanding exactly where the algorithm starts from and how its trajectory goes through and how it avoids bad local minima, and things get more complicated. So what I'm going to do in this talk is to discuss a bunch of recent results, both positive and negative, about local minima and optimization in general in the context of neural networks. I'm going to start in the setting of very simple, shallow, nonlinear networks and see that already there, bad local minima are, maybe unfortunately, surprisingly common. Then I'm going to switch gears and talk about residual networks, where the result there would be of a somewhat different flavor, that maybe there are spurious local minima, but their values are not too bad in a certain sense. And finally, I'll discuss some more recent work in the context of linear networks, which kind of exemplify how even in situations where there are no spurious local minima, such as in the setting that we will consider here, there are still some pretty fundamental hurdles to show some positive algorithmic result for something like gradient descent. OK, so starting with the first part. So what kind of neural networks do we know do not have any spurious local minima? Of course, under reasonable assumptions about the data and the loss. So first of all, linear predictors don't have spurious local minima. This is a very, very special case of neural networks. If the loss is convex, this is a convex optimization problem, and there are no bad local minima. trying to get closer to actual neural networks, so linear networks, which I'm going to return to later on, were also shown not to have local minima. So this is essentially a neural network, but where the nonlinear activation functions are removed. So we just end up with a product of matrices. Of course, in terms of expressiveness, this is the same as a linear predictor, but the point is this is still a non-convex optimization problem in this parameterization, which apparently captures some of the complexity of neural network optimization. Moving to nonlinear networks, we know that for a network composed of a single ReLU neuron, there are no spurious local minima, and also if we talk about the sum of two ReLU neurons. And these are all like results from the last year or two. So the next reasonable step was to talk about the sum of k ReLU neurons, which you can think of as like 1.5 layer neural network. I don't really have a second tunable layer. I'm just summing it up and no bias. But maybe at least for this we can show something. So just to make the setting concrete, we're going to take maybe the simplest setting imaginable, where we try to train such a network on a population objective, where I'm assuming the input comes from a standard Gaussian, and the output is generated by a network with the same architecture. So of course, this can always be, you can always get a zero loss here in principle with the right parameters. And I'm going to assume it's possibly an over-parameterized setting. So the number of neurons that we're using, n here, is equal or larger than the number of neurons in the target network. I should also mention that I'm focusing here on population loss with respect to something like a Gaussian because on Wednesday we're going to hear Suvrit's talk. I don't know if Suvrit is here. Maybe not. So if, judging by the title, he will discuss how you can find spurious local minima usually on finite data sets. But if you talk about some population objective, especially with respect to a smooth loss, things are not that clear. And finally, I'm assuming that the target network, all the neurons are orthogonal, because it seems to make the problem as easy as possible. Now, there were several recent works which tried to show that, at least for this simple setting, the objective has no spurious local minima, but they were all kind of partial. So, if you're close enough to the global minimum or in a certain subset of the parameter space. And what we show is that, unfortunately, this objective does have spurious local minima, at least for certain values of k and n. And moreover, this holds not just when VIs are orthogonal, but even if you choose the weights at random. So if your target network is picked at random, in a certain sense, that still with very high probability you're going to get a local minima. And what might be a little bit unusual about this result is that it's not really a standard mathematical proof. It's a computer-assisted proof with a technique which could potentially be helpful to analyze other non-convex optimization problems. So this is the bad part, but the good part is, as we'll see later, that empirically, if we add some over-parameterization, we allow n to be larger than k, that seems to help very dramatically in terms of removing at least most of these spurious local minima. OK, so what's the challenge in the proof? Why do we need to make it computer-assisted? So the standard way to show that a certain objective has local minima, as we all learned in undergrad calculus, is to take the objective, compute the gradient, equate to 0, find stationary points, and then if the Hessian is positive definite there, it's a local minimum, and if its value is larger than the global minimum, it's a spurious local minimum. The problem here is that although we can write down the objective in closed form, we can write down the gradient, no one has any idea how to compute the roots of this equation. As far as we know, there might not even be a closed form expression to these roots. So that precludes writing down some expression and verifying it's a spurious local minimum. And what we do instead is the following. So although we can't find an exact stationary points, we have algorithms that computationally are pretty good at finding approximate stationary points. So we can run gradient descent until we find a point where the gradient is very close to 0. That's still not a stationary point. It's not a proof. But what we can do is to use a certain certificate that we developed that is mathematically rigorous. It's based on computable quantities, which basically says that if you reach a point where the Hessian is positive definite and the gradient is sufficiently close to 0, then necessarily you reached a point very close to a local minimum. Okay, and then if the value is much larger than the global minimum, it means that there must be somewhere in the neighborhood a spurious local minimum. That also involves some calculations on a computer, but there are ways to do this in a rigorous way that gives you a certificate that the computations are correct. So the proof actually combines, it's a proof, but also an experiment, and the experiments also tell us some other things. So first of all, when we don't have any overparameterization, where n equals k, it turns out that you almost always get stuck in a bad local minima. And the probability, starting from some random point, approaches 100% already when n is a small number like 20. However, once you add just one more neuron, n is k plus 1, then the rate at which you go to 100% becomes much smaller. And in fact, if you add 2 neurons, then actually we couldn't find any spurious local minima whatsoever. So what we can conclude from this is that, on one hand, spurious local minima is something that exists in neural networks, even if we're making all these strong assumptions. Again, Gaussian inputs, just like 1.5-layer network, realizable setting. So it's something that we need to live with, and it can hinder the optimization process. On the other hand, it seems that overparameterization is something that could be very useful. Now, I should say that recently there have been several works which showed for settings other than this that sufficient overparameterization, making the neural network sufficiently large, then gradient-based methods provably find an optimal solution. But I would like to point out that these papers require a huge amount of overparameterization, like high polynomial quantities in the relevant parameters. And at least in our setting, 2 neurons seemed to suffice. So there still seems to be a pretty large gap here between theory and practice in terms of how much overparameterization we need in order to succeed here. OK. So having discussed this, let me shift gears a little bit and, again, try to change the question a bit. So in the experiments we did, I didn't show you them, but the spurious local minima that we found, so it was a probably realizable problem. The global optimal loss is 0. And the spurious local minima we found had a positive value, but not really a very large one, 0.05 or something like that. And that motivated us to consider situations where maybe you have local minima, but in some sense their value are not so bad. They're all located beneath some level set. So to give an extreme example, if you consider an optimization landscape that looks like this picture here of an egg carton, so you have all these valleys. And I claim that this landscape does have a unique global optimum where all the other values correspond to spurious local minima. Why? Because if I take a microscope and measure very, very precisely the width of the cardboard at the bottom of each valley, one of them is probably ever so slightly thinner than the other ones, and that's where the global optimum lies. But if I run gradient descent on this thing and converge into the bottom of one of those valleys, is this really a bad point? Not really. So again, maybe instead of talking about local minima, we can just consider local minima beneath some level set and show that they don't exist. And what I'm going to talk about next are exactly these kinds of results in the context of residual networks. So just as a reminder for those of you maybe who are not familiar with this, so standard networks, you can think of this as stacked units, each of which compute some kind of nonlinear transformation of the input, like a linear transformation plus a ReLU. And in a residual network, the difference is that instead, it's a stack of residual units, which usually take the form here. So the input x is always mapped to itself, plus some nonlinear component. Now, this is an architecture which is very popular nowadays, especially if you want to train very, very deep networks with many layers. And kind of the intuition is that because x is always mapped to, there is this essentially a skip connection. So you can always express the identity transformation by making this g function a 0. And the parameterization is such that it's usually very easy to do. Just take all the weights and put it at 0. So essentially, we only need to fit kind of a residual. X plus some residual term. And the end result is a network where the trained residual unit is no worse than an identity. Right? We can always maybe make G 0, and then the layer kind of disappears. It just does the identity transformation. But maybe by this nonlinear G, we can improve things. So that's the intuition that was associated with residual networks all along, but it doesn't really have any theoretical justification. So sure, in terms of expressiveness, maybe you can always express the identity, but who knows? Maybe we do gradient descent, and we end up getting stuck at some arbitrarily bad local minima. So this is kind of the motivating question, and the kind of residual network that we're going to study is the following. So it's going to be a single nonlinear residual unit, which could be arbitrarily deep. Okay, so its x maps to W transpose times the residual unit. So W is just like a linear output layer. And this G can be pretty much arbitrary. Okay, it could be a 100-layer convolutional network, for example. The only assumption that we're going to make on it is that its last layer is linear, which is a reasonable assumption. It's actually recommended in the literature. So instead of G, we're going to write it as V times f of theta, where V is the linear last layer, and f of theta is all the layers that precedes it, parameterized by some theta. And the optimization problem is that we take this kind of network and take some data, and we want to minimize the average or expected loss for this network for any kind of loss which is twice differentiable and convex in the prediction. So for example, logistic loss or cross entropy definitely satisfies it. However, in terms of the parameters, this is definitely a non-convex problem. And moreover, I'm not even assuming that it's differentiable in all of the parameters. So maybe this theta encodes some ReLUs, which are not differentiable everywhere. And that's still OK. OK, and the main question here, so going back to the motivation of residual networks, that you can always make the residual part 0. So for this network, the reasonable thing to compete with is if I take the residual part, this VF theta, and make it 0, and then I just end up with a linear predictor. So the main question is, for this non-convex optimization problem, are there any local minima whose value is larger than the best that we can obtain with a linear predictor? Just x maps to W transpose x. OK, that's the level set. And we're asking, are there any local minima above that level set? OK? And our main result is the following. So as long as our objective function and its gradient in Hessian with respect to W and V are Lipschitz continuous with any Lipschitz parameter on some bounded subset of the domain, then indeed every local minimum of this objective has a value at most the best that we can obtain with a linear predictor. And I'd like to emphasize I'm making no assumptions whatsoever here about the data distribution. No assumptions about the internal architecture. Again, it could be a 100-layer convolutional network. And again, I'm not assuming that this function is differentiable in all the parameters. So when I talk about gradients and Hessians, I only talk about the gradient and Hessian with respect to the W and V parameters, with respect to which the function is differentiable by definition, right? If we look at its form, L is convex and twice differentiable, so this is definitely twice differentiable in W and V. Okay? So in fact, we can give a more quantitative version of this. So if you take any point of bounded norm, which is an epsilon second-order stationary point, so that is any point where the gradient is close enough to 0 and the Hessian is close enough to being positive semi-definite, then the value is at most the best possible you can obtain with a linear predictor, plus something that scales with this epsilon. Okay? And of course, any local minima is an epsilon second-order stationary point with epsilon equals to 0. That's how we get the previous result. Now, I'm not going to go into the proof details. It's a little bit technical, but kind of the rough idea is that we take the gradient of this function with respect to W and V and analyze its inner product with certain vectors which are carefully constructed so that the inner product, after you massage it a little, kind of magically leads to something that you can lower bound by the suboptimality with respect to a linear predictor. So as long as you're above what you can obtain with a linear predictor, the gradient, for example, is non-zero, so there is some direction in which you can go down, so it can be a local minimum. That's kind of the spirit of the argument. Now, one thing I would like to emphasize is that these results do not imply that gradient descent would work. And this is actually something that you see quite often in the literature, maybe not by the people attending here, but you sometimes see this argument, oh, this problem has no local minima, so gradient descent works, but it's definitely not the case. And you can also see it here. So what can we say based on our result? So it's a result for epsilon second-order stationary points, and we know that in finite time, at least with some smoothness assumptions, gradient-based methods do converge to epsilon second-order stationary points. And we showed that these points are almost optimal compared to linear predictors. But this is only if you assume that your domain is bounded. Okay, so in this O notation, I'm hiding stuff depending on the radius of the domain. And if you run gradient descent, no one guarantees in general that the algorithm would remain in some bounded domain. Maybe the parameters diverge to infinity. And it's really not just an artifact of the analysis. Now, one kind of common trick to ensure boundedness is to add some regularization, right? We add something like the norm squared of the parameters, and then you do a gradient descent. You can't get too far away. But here, it can break things. So you can actually take even a very special case of the kind of functions we are considering, something you can see on the left plot here. It corresponds, you can show it corresponds to a data set where a linear predictor achieves 0 loss. And here, indeed, there are no spurious local minima. But once you add some L2 regularization, then suddenly local minima start to appear, and things break down. OK, so on one hand, again, these results do not imply that gradient descent would work. On the other hand, we can show a positive algorithmic result under the assumption that we tweak the architecture a little bit. So the only change I'm going to do is kind of decouple the linear and nonlinear component of the objective. So now instead of this matrix V and W multiplying everything from outside, I have two different parameters, the parameter vectors W and V, and the V multiplies the F theta. OK? And I'm going to consider standard plain vanilla stochastic gradient descent on a convex any kind of convex parameter set of bounded diameter, where I just run it on an IID stream of examples coming from my desired distribution. And what we can show is that under mild assumptions, basically that the gradients are not too large, et cetera, then with high probability, after at most t iterations, capital T iterations, we're going to find a set of parameters which is almost competitive with any fixed linear predictor of a bounded norm. OK? So you run plain standard gradient descent for long enough, you're going to get something which is at least not significantly worse than linear predictors. Now, the proof of this theorem is not complicated. In fact, it's actually trivial. It's a corollary of an existing result, just not a result in like an area that you would expect. So it actually comes from adversarial online learning. So one of the basic results in adversarial online learning, it says the following. So one way I like to think about it is that stochastic gradient descent is actually a much, much stronger algorithm than what the standard analyses in optimization tell us. So in optimization, you consider stochastic gradient descent as some algorithm which each time takes a stochastic gradient step. But it turns out that if instead you run this algorithm, you just hit it with a stream of arbitrary convex and Lipschitz functions. There doesn't have to be any statistical relationship between them. Then I can't tell you what the algorithm would converge to, if at all. But what it is possible to show is this kind of regret bound, that the sequence of iterates, Z1, Z2, and so on, produced by the algorithm, has an average objective value on the stream of functions, h1, h2, and so on, that is at most 1 over square root of t larger than what you can obtain with any fixed point z star of a bounded norm. OK? And our proof is just a corollary of this. Why? So what we're going to do is we're going to consider these functions ht to be exactly what I defined in the previous slide that we're doing. So we're taking this nonlinear network and hit it with example xt, yt. And notice that because of our architecture, this is a convex. So it's only a function of w and v, the way I define it. Theta t is like I consider it as something fixed and arbitrary. And it's convex in w and v, right? Moreover, if I now take z star in the theorem to be just w and 0, where I make v 0 so the nonlinear part disappears, so just plugging it in, I get this kind of regret bound. And I'm guaranteed that this thing would be at most 1 over square root of t. OK, so I'm kind of avoiding trying to understand what this theta t does. OK, it's complicated. It might be some big network. It does weird things. But I don't care. I'm just assuming that it behaves in some arbitrary way. I just sort of drill it into the loss, plug it into the result, and we get this guarantee. And now it's just a matter of using pretty standard martingale arguments to say that each time in our setting xt, yt is an IID example. So the left-hand side would equal essentially the expectation over the xt's, yt's. So it's going to be, for each t, the objective function with respect to wt, vt, and theta t, minus expectation here over xt, yt. And that's just the objective for the linear predictor w. So overall, I get that an average of these suboptimalities is at most 1 over square root of t. Hence, there must be some iteration where the suboptimality is less than 1 over square root of t. OK, that's the entire proof. OK, so just an interim summary. So we talked about residual networks. We showed how residual units have no spurious local minima worse than a linear predictor. On the other hand, it does not imply that optimization actually succeeds. It's just a geometric statement. But with a small tweak to the architecture, we can say something for standard stochastic gradient descent. What I'm going to do next in the last part is to show another example of this gap between nice geometry and hurdles with optimization in the context of linear networks. So as I said, linear networks is basically just the input multiplied by a product of matrices, for example, something like this. It just reparameterizes linear predictors, and it's possible to show that the geometry is nice in the sense that there are no spurious local minima. Also, we know for two-layer linear networks that gradient descent with random initialization succeeds. This was in a paper by Du, Hu, and Jason Lee last year. But for more than two layers, the situation is not as clear. So there's been several recent works on that. But all of them didn't quite apply to gradient descent and random initialization in finite time. So Bartlett, Fidlong, and Helmboldt analyzed this when all the WIs are initialized exactly at the identity. G and Tilgarsky, in a very nice paper, which I guess we'll hear about later in the workshop, analyze this, but in an asymptotic setting, so asymptotic as opposed to understanding how many iterations we need. And Aurora, Golowich, Cohen, and Hu analyzed this setting for deep networks, but not for standard random initialization, but something which is more complicated. So to understand what we can say here, I'm going to consider a very, very special case of linear networks where all these matrices are just scalars. Okay, so then essentially we're trying to optimize this kind of objective where we have some convex loss, and it's a function of product of these scalars. Now, of course, this is a very special case. No one is really practically interested in such a network, but if we want to understand linear networks in general and be able to analyze them, at least we should be able to analyze these kinds of very simple networks. And consider gradient descent with kind of the standard initializations, either Xavier or close to the identity, which is motivated by making these networks equivalent to linear residual networks. Won't go into the details. Our main result is that already for these very, very, very special simple networks, and under extremely mild conditions on the loss, this algorithm takes exponentially many iterations to converge. That is exponential in the depth. And this is basically tight, both as an upper bound and the lower bound. So what does this imply? So this does not mean that gradient descent fails on linear networks in general. In practice, it does usually succeed, but on much larger networks. So what this tells us is that if you want to show some positive result for linear networks, you somehow have to take the width into account. Somehow take the dimension of the matrices into account in the analysis, and that's not something that we currently know how to do with the current analysis. They all are kind of dimension-free and work for networks of any, for matrices of any size, or do not apply to standard initialization. So, if you want to show a positive result for linear networks, either you need to explicitly use the width being larger than 1, or you won't be able to get something better than exponential in the depth. I'll talk a little bit about the proof ideas. So kind of the prototypical hard function here, although it can be generalized, is when we take something like the squared loss and try to optimize a function which looks like this. Now, geometrically, the difficulty here is that if you take any point where a lot of these WIs are 0, then you are at what is known as a high-order saddle point. So all of the derivatives up to order of k is going to be 0. And moreover, you're going to be surrounded by a very flat region where the gradients are exponentially small in the depth. And if you get stuck in these regions, at least with the gradient-based method, you're generally screwed, because the gradient will be very, very close to 0. OK, so starting with the standard Xavier initialization, so in our setting, this would correspond to initializing each WI, IID from some mean 0, variance 1 distribution. The motivation to this kind of initialization is that it keeps the variance of everything bounded. And indeed, in our setting, the second moment of what this network computes is going to be a 1, regardless of how the depth is. But actually, if you consider other moments of what you get, for example, you don't look at the output squared, but like the absolute value, it turns out that with extremely high probability, you're going to get something exponentially small in the depth. So it's not a well-behaved distribution at all. And this is just a consequence of Jensen's inequality. If we force the distribution of each W to have a mean 0 and variance 1, then it means that in expectation, the absolute value is going to be strictly smaller than 1. So for a Gaussian, it would be 0.9 or something like that. So the expectation of the product of these things is just going to be the expectation to the kth power, and it's getting exponentially small. And that would mean that you're exactly going to initialize in these problematic high-order saddle points, or at least very near to them, the type we talked about earlier. So eventually, you will succeed. You will escape them, but it'll take you exponential time. I should note that this kind of related issue has been noted before, that the distribution induced by Xavier initialization is not always well behaved. So this motivated, for instance, orthogonal initializations, where you force the matrix to be orthogonal. But it turns out that for this special case of one-dimensional networks, kind of remedies that were proposed won't work here. So you really get a problem here with where you initialize.
What happens if you initialize such that the typical values of the one? And do we IID such that?
OK, so this is the next slide. So what happens if you initialize so that all the WIs are, say, close to 1? OK, this is like the other kind of main initialization that was considered. I should point out, I'm not claiming that this problem is hard no matter how you initialize. But at least for standard initializations, it seems that you get a problem. Instead of showing the proof, let me just show you by experiment what goes wrong here. So suppose I'm starting with all the W's close to 1, and this is how the gradient descent dynamics look like. On the left, and I just ran this algorithm when the depth was 7. On the left figure, we see how the objective looks like as a function of time. So we see it goes pretty quickly from 2 to 1, then gets stuck, and eventually goes down to 0. But this intermediate regime takes a long time. It's actually exponential in the depth. And the reason is quite simple once you plot how the individual parameters, W1, W2 till W7, behave. So you start with each WI being 1 plus some small random number. And you want to make, gradient descent wants to make this small. How do you make it small? You want to make this product be as close as possible to -1. So initially, all the WIs decrease. But as they decrease, it means that their product becomes very, very, very close to 0. And this is exactly this intermediate phase here. So they all become very close to 0. The gradient becomes exponentially small in the depth. Now, eventually, there is some kind of symmetry breaking going on here. And one of the WIs is going to become negative. Once it becomes negative, then the product becomes negative. And now gradient descent, instead of trying to shrink the WIs, it starts to increase their magnitude. OK, and then things start to converge, and everything is OK. But the time till it happens is exponential in the depth. OK, that's the proof idea. Now, this analysis is just for, we can rigorously prove it only for one dimension, but we can also do experiments for larger networks. And this kind of phenomena can also occur in higher dimensions. So for example, if I take the natural higher dimensional analog of the function I showed earlier, where now instead of scalars, I have 25 by 25 matrices, then we did the following. So we ran gradient descent with standard random initialization and we waited until one of two things happened. Either the objective became smaller than some reasonable parameters, 0.1 here, or we timed out at 1 billion iterations. Now, 1 billion iterations is a ridiculously large number for this kind of problem, where I just have a few 25 by 25 matrices. And we got the following. So first, starting with Xavier initialization. So what you can see here is for different choices of the depth of the network, of k, what was the log number of iterations until one of these two stopping conditions held. And it's very clear that this is linear, which means exactly that the dependence on the depth is exponential, right? It's a semi-log plot. The arrows here mean percentage of runs where we didn't get convergence. So like even after 1 billion iterations, the objective was still larger than 0.1. And already at depth 8, around 30% of our runs didn't converge. Regarding near identity initialization, things are a little bit more subtle. So if we took the variance to be large enough, something like 1 over dimension times depth, which is just about the largest you can take while still making things not explode with the depth or width, then actually gradient descent did work reasonably well. It still took many iterations to converge, but at some point, adding more depth didn't really hurt performance. On the other hand, if we took even a somewhat smaller variance, but still, like polynomially large in the relevant parameters, so something like 1 over depth times width squared, then we were back in this kind of exponential dependence on the depth. Now, again, it could be that you can come up with an analysis where the precise polynomial dependence on the variance allows you to converge in polynomial time. But again, it's not something that it seems we currently know how to do with the existing techniques. Yeah?
What would happen with anything here in the multi-D case?
So you mean like orthogonal initialization? So in the multidimensional case, we tried it, and it usually worked OK. I should mention, like in general, like if you try other kind of objectives, usually gradient descent worked fine. But again, like if you want to show positive results, you need to explain to me in what way is this function different than other functions where things do succeed. So yeah, at least for near identity initialization and Xavier, things didn't work too well here. Any other questions? Yeah.
Would you expect that if you're running stochastically descent, like if you had some amount of noise in the descent process, that you would just
So it could be, but again, that would mean that you would need to utilize something about the randomness of the process, which is not something that we know how to do with the existing analysis. So, with existing analysis, if SGD with random initialization works, then also gradient descent with random initialization works, at least for these kinds of linear networks. So yeah, it could be that you can show a positive result for SGD, but then somehow you need to take the noise term into account, which is not something that at least currently we know how to do. Any other questions? OK, so just to wrap up, so I talked about a bunch of results, both positive and negative in various settings. And maybe kind of the take-home messages is that, first of all, spurious local minima are common, and they exist even already for very, very simple networks. And it's just something that we'll need to live with. On the other hand, it seems that overparameterization is a very useful tool in at least reducing them. And trying to understand the value of the spurious local minima, not just whether they exist or not, could be helpful. If you just consider spurious local minima above some level set, maybe you can say much stronger things. And finally, no spurious local minima does not in any way imply that gradient descent works, and there are still a lot of hurdles to get from this result, this kind of geometric result, to this kind of algorithmic result. So I think I'll stop here and take questions. Thanks.
Questions?
Yeah.
Very interesting. I have a question about the first part.
Mm-hmm.
So you said that for random VIs, you don't, but then the numerical, if I understand correctly, the numerical proof is for specific VIs. So can you actually make
Yes.
for random VIs? Or?
Yes, the argument is very simple. In large enough dimensions, if you take random VIs, they are going to be almost orthogonal. So once you show something for exactly orthogonal vectors, and now you perturb them a little bit, you can show that the geometry doesn't change too much. So,
Okay, and then related to that, now,
okay.
if you go to overparameterization with a tiny bit of overparameterization, like in k, forget your k plus 2, then if VIs are orthogonal, or random orthogonal, which is the same thing, then you're fine. Do you know what happens if they start being slightly less orthogonal? Do things break down? How quickly do things break down? I mean, break down, right?
So I don't know. My guess is that they would need to be pretty close together for things to break down, but it's just an intuition. We didn't experiment with it too much.
So in the first part, you mentioned that empirically all these spurious local minima are very, very close to the global minimum. And then the second part, you proved that under the level set by the linear predictor, there's no spurious one. But like, how far is the level set for the linear predictor to say what you see empirically, or do you think we can reduce that argument further to a value which is much closer to the global minimum?
Yeah, so on realistic data sets, like the kind at which deep residual networks excel, linear predictors are not that good. I'm not claiming that this has any immediate practical relevance, but we started with one residual unit for which the reasonable thing to compete with is a linear predictor. And yeah, it's natural to ask now, what happens if I compose two residual units or more and then compare? We still don't have results in this direction, but might be possible.
Okay, any more questions? Okay, so we will have now a coffee break until, I'm blanking out. I think 11:15. Well, it's on the program. And yeah, thanks Ohad for a great talk.